All right, everyone. Thanks for being here. Sorry for being so far away from you guys, but I'm going to mostly cut, so I didn't want to be on this very awkward podium. So today we're going to talk about two fairly successful projects and try and make the best out of the two by integrating them as well as possible. My name is Emmanuel Bernard. I'm part of one of the Hibernate core guys, and Hibernate being more than one project. And I'm essentially working on everything related to data inside Red Hat middleware. So you're probably familiar with Hibernate, the object relational mapper, and that's what you call Hibernate. But actually, Hibernate has more than one project behind the same banner. And one of them is Hibernate Search, which is essentially an object index mapper. So we take an object or an object graph and we create inverted index out of them. And we've got two backends. One is the Lucene backend, which actually go and create the Lucene index. And we actually introduced another one, which is the Elasticsearch backend. And that's what we're going to talk about today. And we've got several sources of changes that we can enlist to. And the main one is Hibernate ORM. So Hibernate ORM knows when it has to apply an update or an insert on a project, on an object. And the way to do that is, and knowing that, it actually can send an event to library that would want to listen to that. And Hibernate Search actually listens to those events so that every change you apply via Hibernate to the database is also applied to the inverted index. So you've got those two systems in sync, even though out of the box they are actually not synchronized. An Elasticsearch is essentially a full-text search server that is using Lucene, the library, but make a server out of that, a service out of that. And the cool thing about it is that it speaks JSON on top of HTTP, so you can really call it from any of the software stack you have around, okay? So that being said, I suppose, do you know about Hibernate? Okay, do you know about Elasticsearch? Okay, sorry. We're in the good room. Let's go. The rest is going to be an in-action work. You can go get the demo by getting a picture of that thing. Forgot the name. Otherwise, just go to GitHub. Okay, so this is a JPA. So what we're going to do is start with a legacy application that just used the JPQL to do queries, see some of the limits, and then add Elasticsearch manually and try and see how to do that and the kind of problems we have. And then we're going to add the actual proper integration and see how awesome that is. So yeah, if you have to leave, the end result is that it's awesome, so let's use the integration together. So that's a simple domain model. So we've got video game here, which is an entity with title, description, rating, an associated object publisher, which has name and address. It's got a collection, so a video game has a list of characters associated to it, and what's interesting is that the character also has links back to the video games they belong to. So some characters can be in more than one video game, like Mario is in quite a bunch of video games. And then what simulates the application here is this unit test that says, okay, I'm going to create an entity manager factory out of the JPA. So if you're in Java EE or Spring, this kind of stuff is done for you. But what's interesting is the core of the application, which is, okay, within a transaction, what I'm going to do is create a couple of characters and then create a couple of video games, especially Revenge of the Samurai, which we're going to do our search on top of. So keep that in mind. Create those three games and the three characters, link them together, because we are within a transaction. When we commit, all of the changes are applied to the database, and we're good to go. And the unit tests are essentially just a JPQL query, again, done within a transaction, where we say, okay, give me all of the video games where the title is exactly Revenge of the Samurai. So that's easy. That's what relational databases are for, and SQL are for. If you want to search for one specific term, well, that's a little bit more convoluted. You need to use the like operator and using the percentage before and after. That's going to create either an index scan or a full table scan, right? So it's not necessarily going to be the most efficient way to navigate information. I mean, at least to get it fast. The worst is that when you don't know exactly in which order, if you want to search for more than one word and you don't know exactly in which order to retrieve them, or if they are not capitalized, things like that, right? And here, SQL shows its limit. So you could use the native, full text technology that some of the databases offer, or you could use something like Lucene or Elasticsearch. So we're going to use Elasticsearch. I'm going to cheat a little bit for the sake of time. Let's make that bigger. Okay, so here I've got an Elasticsearch node running. And what I'm going to do is check out the Elasticsearch version of that application. What has changed? So let's first look at the POM, which has two dependencies, one on the Elasticsearch client and then one on the Jackson client, because Elasticsearch speaking JSON, we need to transfer our object graph into JSON before shipping it to our friend at Elasticsearch. And then when we look at how we start the application, so we start the entity manager factory, but we also have to start the JSON binding object, and also we have to start connect the client, Elasticsearch client, to the Elasticsearch server. We use, in this case, the transport client library that they have, and we connect to port 9300. And then the piece of code looks very much like the same, except that every time we persist a video game, we say, okay, let's also index that video game object. And to do that, we are going to take the Jackson mapper, take the object, convert it into a JSON object, and then pass that information to the client and go and call it. What happens if we have an error? Well, we've got a choice. We could say, okay, well, that's probably not the right choice, just print the stack trace. But let's say we could propagate the exception, which means the transaction will be rolled back, okay? So the database transaction will see, okay, never mind, I'll never create this video game object. And the index will, not have changed. It gets a bit more complicated when you start having a second game within the same transaction, because what's happening here is that the first game is pushed to the database within the same transaction, then an index is pushed, index change is pushed, and then we create the second game, and then we try to push the second index change, and then an error happens. And while we can actually roll back the transaction from the relational database point of view, you cannot roll back the Elasticsearch indexing operation, at least not in an atomic fashion. So you would have to find a strategy to compensate things. So anyway, the logic is to say every time I save a video game, I will also go and index the information. How to do the mapping? It's pretty much vanilla Jackson usage. So just by default, all of the properties will be pushed to the JSON, and I might decide to ignore some of them. In this case, I'll also index the publisher and index the characters. So a video game has a list of characters, which will be part of the JSON payload. What we had to do is to put a JSON ignore here. Why? Because when you are going from the video game to the character, if the character has a link back to the video game, then Jackson doesn't stop this infinite loop. So you get an infinitely big JSON object, or you get a out-of-memory exception, more likely the second, right? So here we decided to cut the link at that level. The other problem you have is this one. Here we are just creating objects, so that's fine. But let's imagine I'm changing this character, Luigi, and it's changing its special power for another one. When we index the information from the video game, we actually embed the information of character in it. The JSON object is really video game and all of the characters associated to it. So if I change one of the characters, I have to go back to each of the video games that the character plays in and then update the video game object. So in my code, I will have to do that kind of manual work every time I change the character. So it's additional work for you to do. But the good thing is then our query system is much nicer. If we look at, well, let's go straight to some more complex one. Okay, this one. So you use the Elasticsearch client and you say, okay, I'm going to query on this video game index, which is the one where we push the information initially, And I'm going to write a query that says, please find matching result on the field title and with this text, Samurai and Revenge, in reverse order compared to the title. But because we have this inverted index technology, we're going to have to, we will get results. And what Elasticsearch returns is essentially an array of JSON payload that do represent the results matching the object, and the most interesting one at the top. So what you have to do is take these JSON payload for each of the results and convert them back into a video game object, which Jackson is going to do for you, and you got this array of video game objects. Two things, though. This video game object is actually not a Hibernate managed object, so if I do a change to that video game, the change will not be propagated. And the second problem is that if I take the video game and I go from video game to characters, and then for a given character go to video game and so on, I don't have the lazy association and the graph navigation that Hibernate provides. I just have what the JSON object had. If I want to then go for the navigation, I probably will have to go and fetch the object by its ID from the database and then continue navigating, okay? Let's actually run to prove you that I'm not just talking nonsense here. This should start the unit test and go and index information into our friend Elasticsearch. If we look at Elasticsearch and the what's indexed, what you have is what is called a mapping that says, hey, for the index video game, I'm indexing stuff of type, this fully qualified class name, and I've got several properties, and they are actually indexed using default analyzers. If you want to custom that, and very quickly you will have to custom things. If you want to do approximation, you might want to do n-gram or phonetic approximation, and that requires different analyzer. Maybe you're playing with different language and whatnot. Here you will have to not rely on the default settings auto-created by Elasticsearch, but you will probably customize this JSON mapping essentially to add the analyzer you actually want to use. So you will likely get this JSON structure and store that in your Git repository or whatever source system you're using, and you will have to keep in sync both your object model and that structure and make them evolve together. Okay. So I've been complaining about a few things. So can I do better? And that's the idea of that demo. So I'm going to start not from scratch, but I go back to the legacy approach, and I'm pre-configuring things like the POM and whatnot, okay? But we start from a non-working, Hibernate Search, Elasticsearch integration. So let's look at the POM. So instead of having the Jackson and Elasticsearch library dependency, we have a dependency on Hibernate Search ORM because we integrate between Hibernate ORM and Hibernate Search. And we also have a dependency between with the module Hibernate Search Elasticsearch, which actually use Elasticsearch as a backend. So that's cool. How do I configure that? Well, actually, Hibernate Search you don't bootstrap Hibernate Search manually. It's actually bootstrapped by Hibernate ORM itself. So the way you put configuration is via things like the persistence.xml or your Spring property file and whatnot. So you can see 4 properties that are related to Hibernate Search here. First of all, we use Elasticsearch and not the Lucene backend. Second, we point to the actual Elasticsearch instance. In this case, we use 9200, which is their REST endpoint instead of the transport. Why do we do that? Well, we didn't want to be tied to a specific version of Elasticsearch, and the library tends to be tightly coupled with the version of Elasticsearch. So we wanted that flexibility. And they do recommend that kind of approach nowadays. And they're actually working on a REST-based client library, but it's going to take time. Another things we have is schema management. Remember this JSON payload that represents the mapping? Well, Hibernate has the actual class structure, so it can actually propose something very much like that. And because you can put the analyzer some additional information on your domain model itself, you can actually ask Hibernate Search to say, please use the analyzer foo or bar and so on. So you can actually customize a lot of the way the integration is done. And that mapping will be pushed to Elasticsearch for you. So you don't have to keep that JSON payload on the side of your project. It's just going to be generated by Hibernate Search. And the last point is, because I've just got one instance of Elasticsearch, it's in yellow mode, and we try to be safe from a Hibernate Search point of view, so we don't let you push stuff on a yellow state unless you explicitly say OK. So in this case, I just degraded a bit the quality. The next step I have to do is to actually put some mapping information here. So by default, entities are not indexed, but I can ask them to be indexed. And I just have to say, please, make this entity indexed. And then I'll decide which property exactly I want indexed. So I want the field, the title, I want the description. And maybe for this one, I want a specific analyzer. So I'll define the analyzer with, its name definition. In this case, let's say I'll use the English analyzer, which happens to be defined on the Elasticsearch side. So this is the binding, and that's how we are going to create the mapping that I was describing automatically for you. We do the right type conversion. So if you have a numerical, we do the right numeric conversion. We could deal with dates. It's not interesting here. And for objects, so by default, we don't include stuff in the index because we don't want to pollute too much the index. But if you want when video game is indexed, if you also want to index, for example, the publisher or the list of characters, you have to add the @indexed embedded annotation on it. And all of a sudden, when you index the video game, we also index the characters associated to it. And we don't have to use the @JSON ignore thing for a couple of reasons. So first of all, I haven't added the @index embedded, so by default, this association is not embedded, okay? But even if I had, Hibernate Search is smart enough to say, okay, I'm indexing this video game, and then there is a character, and then the character reference back to the object I was coming from, so I'm going to stop to avoid this infinite loop. So it actually stopped that. You can also define a specific either depth or a specific list of paths that you want to index. So sometimes you want the video game and the list of characters, and then for each of those, the actual video game associated to do a query of like friends or friends kind of thing. So you can define explicitly the path where you want to go. Another problem that Hibernate Search solves is, remember when I was changing the character object in here? What I had to do is remembering that I was updating the character object and then updating manually all of the video games. Well, Hibernate Search does that transparently for you. It knows that a character is associated to the video game, and what you just have to do is add the contained in annotation here to just give him a small hint. So let's see how you actually index information. So no more starting Elasticsearch client, no more Jackson. We just have a regular entity manager factory bootstrap, no Hibernate Search bootstrap. It's actually embedded here transparently for you. And within the transaction, we're creating the object, we are creating the video games. Oh, there is no explicit indexing here. And we do things, and then we commit the transaction and we close. So where is the Hibernate Search code here? It's actually embedded. It's done for you because when those operations happen and when you do the actual flush on Hibernate, the list of changes, creation, update, or suppression of entities is actually passed to Hibernate Search, which will look and say, okay, that's a video game, so I need to update my index, or that's a character, so let me go back to the list of video games and then update those video games. So it does all of that work for you. And it does it in a batch mode. So you start a transaction, and it queues all of the changes that it has to deal with. And instead of applying them right away when you do a persist, it will actually wait until a transaction commits. So if you do a transaction rollback, then this queue is just discarded, and then the index hasn't changed, the database hasn't changed, everybody's happy. If you commit, then we have this list of changes that we can push to Elasticsearch, and we do that using their batch API to make it more efficient and have less back and forth between your application and the Elasticsearch client server. Sorry. What am I missing here? I think I'm pretty good. Indexing. Okay, well, we're ready to do the query then. What What you have to do is create a full text entity manager, which is just a decorator for an entity manager. So you just use this small decorator builder and with the entity manager. It's going to provide you queries, methods like create full text query and things like that. The other stuff we're going to do is provide a query builder, which is going to give us a type-safe way and object-level way to express our queries. You can do actually two types of queries using this high-level query builder or the actual native Elasticsearch query approach. So I'm going to build the query builder for the entity video game, and for that class, get it. And I'm ready to write the query. So let me first start with, first of all, let me use the full text entity manager. And let me first start with the query builder, which is at a higher level and I think nicer. So the way we do it is you say create full text query, and then you can pass a query that you will build with the query builder. So you've got a bunch of options here: range, phrase, spatial query, more like this, which is please compare this object to what you have and give me the one matching. But let's do what the query was doing. So I want to do a query on the field title, and it scales very nicely, so I can add a field description. In this case, I won't do it because it would change the results. And then I want to match samurai, revenge. Creating the query, I'm giving it what index I want to target, the one storing video game, and I'm essentially done. Let me do a small suppress warning here. And check. It's something we're going to fix, but it requires a small backward compatibility change, so it's going to be in the next major version to fix that small unsafe use. So it should work. Let's give it a run. Something that I should have done is to actually do, so it's working, it's all green, awesome. Something I should have done is create pagination, because I do not want to retrieve all 1 million results. And actually, Elasticsearch limits the result to 10,000 by default, but they really want you to give retrieve the first 10 or first 20 or the one you really need. So in this case, we just use the JPA pagination logic and just express them. And by the way, the objects we returned are managed objects. So these are Hibernate objects with the lazy associations, and you can navigate, you can change the objects, and the change will be propagated via Hibernate. So you're back to the same model that you have when you use a JPQL query. Another things we can do, is instead of using the query builder here, is use the native Elasticsearch query. So you just have the small wrapper. You can either use the query string approach or the JSON approach, which is a bit more powerful. I don't fully remember the query, so let me just copy it here. So it's a query, it's literally the same query, in this case with the exact title, but it doesn't really matter. And that's going to work. So you really have the choice to use the native Elasticsearch query or work at the higher level. And the final stuff I want to show you is that I can do something that is called projection. So instead of retrieving the actual managed object, I can say, only retrieve some of the properties. So title, and maybe I want to get the score. The score is the relative result of the relative value or quality of a result with another for a given query. So something that I typically do when I play with search engine is to say, okay, I'm going to display the first result and the rest of the result up to, say, the 10% of the value of that score. So if the 12th result is like less than 10% of the first value, I feel that it's too diluted, and I will stop showing them, for example. So you could do things like that. You could even retrieve the JSON structure. It's called the source in our case. Source, don't know why it is. I'll do some mistake here, so let me not do it. And what you retrieve here is not a video game object, but an array of objects, okay? Because you've got title at the first, element 0, and then score at element 1, and so on. Okay, I think that's what I really wanted to show you. I showed you that the DSL is much more flexible and much more powerful. It scales very well even when the query become complex, so that's very nice. Let me go back to it. So if you have to get an output of that presentation, is that there is a super nice integration. If you use Hibernate ORM and you want to index stuff inside Elasticsearch, then go for the Hibernate Search integration. It will do a lot of nasty and tedious work for you, and you will not miss some of the index or deal with the error and whatnot. And we query at the higher level, which is your object, your domain model, conceptually, even if, of course, we do the mapping. And there is lots more stuff like the error handling, so you could say I'm going to log all of the errors when I'm doing indexing, or I could throw an exception, or I could send a message to somebody and put that in a queue to retry and whatnot. There is a mass indexer, which is going to take all of the data from your database and indexing it as fast as possible to Elasticsearch. So it's a very nice way to do the initial indexing, or even like a regular indexing if you want to refresh information and don't, for some reason, trust the event system and whatnot. Faceting, geolocation, lots of goodies. And of course, because it's a regular Elasticsearch index, you can do native query, play with the higher level things like Kibana and whatnot. So you got all of the goodies from those two tools and bring those two universes into one coherent one. So yeah, have a look at the demo. It shows all of the different phases, and there are like different branches for the steps, like the legacy one, the manual integration with Elasticsearch, and the actual full integration. And I tried to keep a few minutes for questions. So yeah, if you have any questions, just let me know.
So why would they choose this over Lucene?
So the question is, why would I want to choose Elasticsearch over Lucene? So there are pros and cons. Maybe you already have an Elasticsearch cluster and already have centralized stuff around that, so you would prefer to push stuff into Elasticsearch. Maybe your ops team is already familiar with it instead of having to deal with the Lucene thing. Lucene, out of the box, will let you write stuff on, say, a file system. So in Hibernate Search, we have a way to cluster that in a somewhat manual way, but Elasticsearch really wants all of the way to make it clusterable and scalable, so that would be an interesting model. On the other hand, I would possibly, if you have like super low latency requirement, one of the cool stuff about Hibernate Search is that you can keep a copy of the index on each of the application layer, and you would do a local lookup instead of having to go through an external system. So that would be potentially a bit faster. And then you've got access to the actual Lucene API instead of the Elasticsearch API. So in terms of flexibility but complexity, Lucene API, your foundational, can do lots of magic stuff. Then Hibernate Search provides an object level abstraction to it, but lets you give access to the Lucene API if you really need to. And Elasticsearch is pretty complete feature-wise, but of course at a higher level than the plain Lucene API. So that's how I would make a choice. You're welcome.
For the example you had up there around character, that was also indexable. Would it?
That was also what?
If the character entity was also indexable,
Yeah.
would that create two different types and you'd be performing searches on, acting as a foreign key, or would character still be embedded?
So the question is, if character actually had an @indexed annotation on it instead of the contained in that I put. So if we go to character here, if I had put @indexed here, what would happen? So what would happen is, well, first of all, you would no longer need the contained in because we would know about that, but that's kind of a detail. What you will end up having is an indexed character and an indexed video game. So you will have two different indexes, and they are useful because you will be able to apply queries starting from the character or starting from the video game. So the video game will still contain the character, and the character, in this case, because we haven't put the indexed embedded in the video game, you will only have the character information indexed, right? But you could also, like cross streams, essentially. We do not make use of some of the quote-unquote join-ish thingy of Elasticsearch. First of all, because the denormalization we're doing is doing some of what they are doing. It's something we will probably investigate down the road, but there is not a very pressing needs to do that. Any other question? Yeah? Okay, so the question is, are we using are we targeting Elasticsearch 5 or Elasticsearch 2 dot something, 2.4? So the version you have here is actually using Elasticsearch 2.4. We had to make a choice, and they did break a lot of things in 5, so there was we had to, and frankly, we discovered quite a few bugs, so we couldn't map everything. But we are fairly close to actually have, there is a pull request with a working version of Elasticsearch 5, so we're really going to have 2 different backends, one for Elasticsearch 2.4 and one for 5. So I don't know if we will hide that complexity or just let you say 2.4 versus 5, but yes, you will be able to target Elasticsearch 5 and Elasticsearch 4, and hopefully, and that's what they are targeting, they'll try to not break stuff as much as they did, so we will have less problem in the future. But if you want to give it a try, this is literally a pull request. It might already be on master, so it's not in a release yet, but you could experiment and give us some feedback about bugs and whatnot. Maybe one last question? Okay. So go git clone and give it a try. Thank you.